Welcome to Unit 5, Lesson 10. Today, I'm going to tell you about something that is just a very, very brief introduction to piecewise linear functions. And you might be thinking, piecewise linear functions, what does that mean? Well, recognize that linear functions mean that these are going to have straight lines in them and that functions are going to be, every input has its own output. Piecewise is a little bit different. What we're doing is we're taking these functions and we're going to build them out of linear pieces. So literally, we're going to take little chunks of lines and we're going to arrange them all together. And it's going to look, little things like this. So maybe we think about mountains or whatever it is, but each of them, except for that last one, are relatively straight and they represent a function. So no absolute vertical lines or anything like that. I promise that has a little bit of a slope downward this way, but you get the idea. So when we look at this first part of it, notice some wonder lines and dots. What do you notice and what do you wonder? Well, I wonder about why did they put two lines over top of all these dots that kind of curve around. I notice all the dots. I think about all the curves. I wonder why didn't they make a line that follows the dots? Why didn't they do something more like a lot more little pieces to make this work? There's a lot of different things. And today, what I'm hoping to help you to realize is when do we put in little chunks and when do we not? Here's this model, or the recycling model again, that we've seen several times. Our job is to turn this into a piecewise function by drawing 3 to 5, somewhere between 3 and 5 line segments to approximate the graph. So to approximate this is just going to be a way for us to be able to understand the graph just a little bit better. And now starting right here, what we're going to do with it beyond that is we're going to find the slope for each piece and talk about what does the slope tell us. So the first piece that I'm looking at is I see a lot of growth from 1991 to 1996. From 1991, I see that we have an ordered pair here of 1991 and probably about 16%. This is just graphing or rough estimates. And I see that growth peaks right here at 1996. And I'd say it's about 22%. And so what I could do is I could actually draw a little piece that's linear from these 2 points. And I see just a little linear function. And when I look at the graph between those two, I see that there's an increase of 6% over 5 years. And so what we would say with that is our slope for that piece would just be a slope of 6/5. Okay. The next piece, I see a little bit of decrease from here, and it starts to go up right around here. And so I see a decrease down to 1998. We saw it go down just a little bit, maybe to about 21.5%. And so I could draw that little piece right there. And when I use that little piece right there and I look at the slope right there, I see that I've decreased approximately 0.5% over 1 year, which would tell me that's, over 2 years. I don't really want a decimal version in there, so if I were to double that, that would be a decrease of 1/4. And that would represent the same type of slope. Now for the next segment, I see a pretty steady increase all the way through. So I'm going to just go ahead and I'm going to connect all the way up here to 2011. I mean, there might be questionability about right here with this part of it, but I'm going to go ahead and go here to 2011, where we get all the way up to 26%. Now with that 26% of growth, we see a 4% growth from 22% to 26%. Over the period of, let's see here, that was 1998, over a period of 13 years. And so we can see that slope is just a little bit of a different type of slope, but it's how much or how many, the percentage of recycling over that amount of years. So not a lot of increase, not like our first one that we saw, but also took a lot longer time. And then we also see that there's finally a decrease at the very end, where we get to 2013, and we drop down to, looks like about 25% or so. So again, these are just rough estimates. We see a decline of 1% over 2 years. And what you can see with that is we see several different slopes make up these data. And what we can do is we could say, just over these times, we can make generalized statements that talk about what do these slopes tell you. And generalized, they say how much, what percentage of material recycled over short periods of time look like. Okay, so just looking at this and breaking it up into smaller pieces can kind of help us to understand the data just a little bit more, and we can look for trends and we can look for other information that would help us to understand that a little more. Okay, here's another example, talking about dog bath. So Elena filled up the tub and gave her dog a bath, and then she let the water out of the tub. And so this graph shows the amount of water in the tub in gallons as a function of time in minutes. Add labels to the graph to show this. Well, if we're talking about the amount of water in the tub as a function of time, that means that the gallons of water would have to be the piece that is dependent on the amount of time in minutes. There we go. That one's done. Number two, when did she turn off the water faucet? Well, we see right here at 0, 0, there is 0 times 0 gallons of water, and we see that the water is increasing. And I think that's important to note that we're increasing 24 gallons in 6 minutes. I think that's just an important piece to look at. And when did she turn the water faucet, or turn off the water faucet? She turned it off after 6 minutes. And the way that I know that is because the water is no longer increasing, or the gallons are no longer increasing. So how much water was in the tub when she bathed her dog? There was 24 gallons in there. And how long did it take for the tub to drain completely? Well, for the tub to drain completely, we looked at the tub, it filled up all the way, and we could see that it was filled up here for a little while, from 6 minutes to 18 minutes. So that's 12 minutes. So that's 12 minutes of washing. And then we see that the amount of water in here starts to decrease. And so we're talking about from 18 minutes and 24 gallons down to 30 minutes and 0 gallons. So we would just see that piece where we would look at 30 minus 18 equals 12. And so it took 12 minutes to drain. Completely. Now, if we're talking about that piece as well, I might as well, since I already found the constant rate of the filling up, let's go ahead and talk about the draining. So this is talking about a minus 24 gallons in 12 minutes. And what we would do the minus sign for is just simply to state that we are decreasing our amount of water. So there's 2 more questions. Let's look at what those look like here. The next one, at what rate did the faucet fill up the tub? It's almost like I knew what was coming. And when we talk about the rate that we saw to filling it up, we saw 24 gallons over the course of 6 minutes. So 24 gallons in 6 minutes gives us 4 gallons per minute. So the tub is filling up at 4 gallons a minute. Interesting piece, if that tub is filling up at 4 gallons per minute and you are one that's taking a 30-minute shower or a 30-minute bath, you're using 120 gallons of water. That's quite a bit of water. Imagine an hour. Then you can understand why your parents get mad at you. Remember when we were talking about draining the bathtub? It took 24 gallons to drain out, but it only took 12 minutes it took a total of 12 minutes to drain. That means that we're talking about negative 2 gallons per minute. Now you might be thinking, what do you mean negative? How can you have negative gallons? Well, what we're talking about here is we would just say draining 2 gallons per minute. When we're noting this mathematically, we have to understand that the negative number will exist, but then we have to interpret it as draining water at 2 gallons per minute. All right. So we have another graph here that's actually a lot like the one that we just had. It really looks the exact same as this, but it's representing a different story. This graph shows the speed of a car as a function of time. So here's our time and here's our speed. Describe what the person or what a person watching the car would see. Well, what I would see right here, I see a pretty steep slope. I see the speed is increasing over a relatively short amount of time. So I would say this person was stopped right here. Whoops, sorry. Stopped here at the beginning and increased speed rapidly. And then right here at the top, it flattens out. That would mean that our speed over time is maintaining the exact same. So we would say this is a steady speed for a short time. And then we would talk about this person coming right here and saying that they're slowing down at a constant rate to a stop here at the very bottom. But we would say that they're slowing they're slowing down a lot slower than they actually sped up at a slower rate than when speeding up. I don't know why I wrote all this at an angle, but hey, why not? It's kind of fun for me. Okay. The next little section right here is actually kind of a linear model that I really like. I think it's kind of cool. The Ready for More. It says the model will represent the speed of a car as a function of time during a 3-hour trip. And what you'll see with this car is actually something, it's a little bit different. And then the question says, how far did the car go over the course of the trip? When we look at it, we actually see a different kind of piecewise function. When you see a closed-in circle or a filled-in circle, it includes that data point. When we see an open one, it excludes that data point and suggests that it's only information between the 2 points, but when it's filled in, of course, it's including. So from here to here, we would say in those 60 minutes, or probably like 59.9 minutes, and then new data starts. Now, the other thing that we've talked about is the input has to have a unique output. And so you might be saying, well, the input 60 has 2 different outputs. In this case, it does not, because this is an open circle and this is a closed circle. So this could still be a function. So there's a much nicer way that we can actually visualize this quantity in terms of a graph. And what we can do is we can actually start cutting off this information and saying, you know what, they drove 20 miles per hour for 60 minutes, just to right here. And in that 60 minutes, if we know 20 miles in 1 hour, then we would know that they drove for 20 miles at that speed, pretty slow. And then they sped up 10 miles an hour and went that speed for 30 minutes. And so that 30 miles per hour for half an hour, so dividing by 2, is going to tell us that they went 15 miles. When we look at the next segment for 90 minutes to 120 minutes, that's another half of an hour. And in that half of an hour, they're going 50 miles per hour for half of an hour. So 50 divided by 2 means that they've gone 25 miles in that amount of time. And then they went 40 miles an hour for just 1/4 of an hour. So we're going to have 40 divided by 4 gives us 10 more miles. And then they slowed all the way back down to 20 miles per hour again for 1/4 of an hour again for 15 minutes. There's another 5 miles. And then finally ended the trip going 10 miles per hour for 30 minutes. And so we see that 10 miles per hour for 30 minutes. That's half of an hour, which is again 5 more miles. So when we look at all these pieces and we start adding them up, there's 20 plus 15 is 35. Another 25 is going to be 50. 10 more is 60. 10 more is 70. I feel like I didn't add that right. Let me double check that again. There's 20, 35. Nope, that would be 60, 70, 80 miles total. So maybe this is something my family and I, we went to Yellowstone Park recently, actually this last year, And I think this could be something that would be like in Yellowstone Park, where you're actually driving pretty slow, and then you could speed up more, slow down, slow down, slow down, slow down. There's a lot of those different pieces, maybe mountain passes, who knows what it is, but this would be an opportunity to recognize that we can write all of our information and our data in a totally different way than what we're probably used to. So with this, like I said, very brief introduction to piecewise functions. This is just a soft introduction. You'll see more of this in algebra. But this graph shows, this graph right here is showing Andre biking to his friend's house where he hangs out for a little while. And then they bike together to the store to buy some groceries before racing back to Andre's house for movie night. And I like that. That's an interesting thing. Before they go racing back for a while, we see other things like hanging out for a while. And then each line segment of this graph represents the different parts of his trip. So here's Andre just kind of heading to his buddy's house. And then he probably gets to his house, and then they go to the store. And then maybe they're racing back to Andre's house. They stay, or excuse me, let's look at this. Andre is biking to his friend's house where he hangs out for a while. Actually, that hangout is probably more like right here. No? I'm sorry, I'm really goofing this up. Hanging out for a while is probably right here. Going to the store, spending, okay, there we go. So this is going to the friend's house. It's right here. Hanging out at friend's house for a little bit. Going to the store. It's a little bit further away. Shopping at the store, and then racing home. We can see it's racing home because it's quite a bit steeper slope than the rest of it. So these pieces of this function, when we're looking at it, they just piece out the experience of what happened. They can talk about the different speeds that they're riding at. Obviously, he's riding kind of slow to his buddy's house, then he stops riding. His distance doesn't change, but the time changes. Then they ride a little further from his house to his buddy's house. Distance, again, doesn't change for a while. And then the distance returns back to normal when he gets back home. Everything down here on the x-axis would be at home type of thing. So we can use this to start to understand how piecewise functions look, how they interact, and they work with all the systems that we've been working on, talking about linear functions and nonlinear functions and such. The last thing that we could talk about is we can use piecewise functions to represent different stories. We can talk about them using models instead of actual data, or models as actual data. And then we can talk about those segments and those pieces that what they just model and what they represent. I mean, the final thing that we can look at is back to where we started, is taking a look at the time or the temperature of a place over a certain amount of time, where temperature is a function of time. And we can see that hours after midnight, well, 6 hours after midnight, this is at 6 a.m. That was the warmest part of the day, and then it cooled off. Seems a little bit weird, a little bit backwards to me, that that was all the warmer it got, but that's what the data tells us, and so that's how we have to read it. So thanks for checking in. This is our last lesson in this little segment, so we'll see you on the next one.